Yeah. Radius. It's hard to measure the radius of the atom because there's no wall barrier, but basically the size decreases as you go up and right. And so as we go left, the size decreases because, Z effective increases. So as we increase the number of protons, the electrons get pulled in, and we see same shell electrons are not effective shielders. Same shell electrons, not effective shielders. When we go up, the radius decreases because n decreases the number of shells. Electrons. Z effective is fairly constant. And so, n equals 3 to n equals 2, you've just lost that third shell, so the size decreases to go for the same Z, roughly. And so that's the atomic radius term. And so we want to know about the size of atoms, and then there are other things that are related to the size. One of the things that's related to the size is something called ionization energy. Ionization energy, we have I1, which is the first ionization energy. The first ionization is just taking a gaseous atom and then just ionizing it to a positive cation, an electron. So this would be in the gas phase. That would be the ionization energy. So the ionization energy of hydrogen would be a gaseous hydrogen atom being ionized. Now, this is not, if we're looking at hydrogen, we take a gaseous hydrogen atom and then ionize it here from a gaseous ion. But before we can get that gaseous hydrogen, we have to take H2 and break the bond. And so this is called the bond energy. This process here would be I1. This would be additional energy that would be required here to break it. Now hydrogen won't have an I2. Why is that? It doesn't have a second ionization energy because it only has one electron, so that's all it can lose is just one electron. But other species could potentially have more than one electron, like helium. Helium could lose the first electrons, will be I1, and then the second electron, which would be I2. And so I2, would be the second ionization energy, which we call I2. That would be A, if there is additional electrons to be lost, we form A2 plus an electron, etc. Just follow that pattern. And so when we look at the ionization energies, it turns out that the smaller the atom is, the harder it is to ionize. And that makes sense because the smaller an atom is, the more the electrons are being pulled into the nucleus because of a higher Z effective, usually. And so, you can see that here. And so the ionization energies would follow, the same pattern here, in which if we look at the ionization energies, well, let's look at I1 though, because I2, etc., is more tricky. So I1 increases as we go up and right, And so which species should have the highest ionization energy? Well, it should be the smallest atom. What's the smallest atom? Helium. And so helium has the highest ionization energy. Let's get this. Now, the ionization energies, they're going to show, that's a general trend. They're going to show small deviations in that general trend. So, if we just pick a shell or pick a period here, let's go across the second period or the second shell here. And so, an example of this would be we start off with lithium versus beryllium. Which one has a higher I1, ionization energy 1? Lithium or beryllium? A beryllium should have a higher ionization energy because it's smaller, correct? And I should have gone to the outside. Then we go from beryllium to boron. And so we say that beryllium has a higher ionization energy. And then we go to beryllium to boron. Which one has a higher ionization energy? Boron. Boron should have a higher ionization energy. But it turns out that it has a lower ionization energy. And so this is one of those little, it's not that much lower. I mean, it's not super significant in the sense that we expect this because it's smaller, and so it should, but there's a difference. So we have to look at it in more detail. Here, when we're at beryllium, we have our nucleus, which is in the center, and then we have 2 electrons here. And so we're ionizing one of these electrons. You just pick one. This is a 2s orbital. So we're looking at the 2s orbital with 2 electrons in it. And we remove one of these electrons now. For boron, we're doing a, which one would we ionize? A 2s electron, which we have 2 of those 2s electrons. I'm not showing all the electrons right here. I'm just showing the valence electrons. And so we got the 2s electrons here, but we also have 2p electrons. That's one 2p electron. And so what do you think is going to be easier to ionize, a 2s electron or a 2p electron? 2p electron. 2p electron is going to be easier to ionize because it's less penetrating, more shielded. And so there's a slight drop in ionization energy because we're ionizing a 2p, which turns out to be a little easier than a 2s electron. And so that's it. And so what does this blip look like in ionization energy? We can take a look at it graphically here. This is what the blip looks like. We go from lithium to beryllium, it goes up, but then do you see this little blip down? Even though boron's smaller, we expect it up here, but it's not. It's because it's 2p electron. 2p electrons more shielded, less penetrating. But then once we go from boron to carbon, then it falls back into place. Is carbon, we got to do a 2p, so it's a 2p electron versus a 2p electron, and so carbon's smaller, therefore it should be harder to ionize. And then from carbon to nitrogen, nitrogen's smaller, right? And so it's harder to ionize. And then we go to oxygen, oxygen's smaller, And so it should be harder to ionize. And so here we're at lithium, the beryllium, and the boron, the carbon, nitrogen. But look at what happens when we go from nitrogen to oxygen. Do you see that little blip? And so it turns out that we expect this, but it turns out that we drop down in ionization energy. And so why is that? Why that is because of this. If we look at nitrogen, I'll draw the energy level diagram just for the energy level diagram. It's 1s, 2s, 2. And then we look at the 2p, 1, 2, 3. That would be it. And so when we're ionizing nitrogen, we're taking any one of these 2p electrons and stripping it off. And so this would be for nitrogen. But when we go to oxygen, let's take a look. What happens with oxygen? When we go to oxygen, 1s, 2s, and then we go to the 2p here. And it looks a little bit different. When we go to oxygen, this is what it looks like. In the valence shell, which is the outermost shell with 2s, 2p, we have 2, 4, 6 electrons, whereas nitrogen only has 2, 4, 5 electrons in the valence shell. 2 core electrons. And so what's the difference here? What's the difference is I don't pick any 2p electron, I pick one specifically. Which one do you think would be the easiest to ionize? The easiest one to ionize is this paired electron here. The reason the paired electron is going to be easiest to ionize is because of electron-electron repulsions. Both electrons are the same charge, and so there's going to be a little bit of help here in the sense that the electron-electron repulsions are going to make it easier to ionize. And so electron-electron repulsion is a reason why. Because we don't have this electron-electron repulsion in nitrogen. Nitrogen is just singly occupied in the 2p's. But when we go to, from oxygen, we go to fluorine. Fluorine jumps up again, like we'd expect. But with fluorine, it jumps up because now we're comparing oxygen with fluorine. Both of them are going to have electron-electron repulsion because fluorine's going to have another electron here, so it could take any of those paired electrons. And fluorine's smaller, therefore it's going to be harder to ionize. And then finally, neon. Neon should be the smallest of this series and the hardest to ionize. And so the species with the highest ionization energy on the periodic table, neutral species here, is helium. This is for I1 only, the first ionization energy. Second ionization energies are going to be even harder to do. Okay, but you see that blip. Now take a look at what happens in the third period. Do you see when we go sodium to magnesium, and then magnesium to aluminum, there's a huge, huge drop here like we expect. We don't expect that huge of a drop. But up here, it's a much smaller drop. And then when we go to the third period, the drop, the changes aren't. This third period, you've got to add the d electrons in here as well. And so adding those in, we don't see much of a blip here, there's a blip there. And so with the d electrons here, well, we got this blip here, but this blip is less pronounced. It turns out that, you kind of expect things to be less pronounced as we go on to higher and higher periods because the atoms get larger and larger. As the atoms get larger, this effect isn't as significant, but it's hard to see because this is a pretty big drop here. But anyway, what you want to know is you want to know this, what causes these two blips here. Otherwise, the general trend will just take as is. That is, the smaller the atom, the higher the ionization energy, with two exceptions that you should memorize. And those exceptions, the pattern is kind of repeated, as we go across here. And so here, with relatively few exceptions, ionization energies increase from left to right across a period. Well, we just have two exceptions there. Boron and oxygen. And decrease from top to bottom within a group. They're going to decrease because as the atoms get bigger, it should be easier to ionize. Ionization energy decreases, atomic radii increase. And so that's just saying the opposite of this. Ionization energy is going to decrease as we get bigger and bigger. The biggest atoms are where? From the bottom left, periodic table. So let's take a look at some of the ionization energies in terms of numbers here. Like sodium. Sodium is about 500. That's the first. And then it increases to magnesium. But when we go from magnesium to aluminum, it drops. Do you see that drop? Why is that drop there?
P orbit?
Yeah, we're ionizing a P rather than an F. But then it increases again until we get to phosphorus to sulfur. It drops here. Why is that?
Paired electron?
Yeah, paired electron versus unpaired electron. Paired electron, we have electron-electron repulsions. Those electron-electron repulsions decrease as the size of the orbital gets bigger. As the size of the orbital gets bigger and bigger, then electrons interfere with each other less and less. Now, argon's going to have the highest here, 15, 20. We look at the second ionization energy. Look at the second ionization energy for sodium. It increases significantly. To ionize the second electron is going to cost you like 5,000 kilojoules versus 500. So it's 10-fold increase in ionization energy. And that tells us something. That's a huge amount of energy. So it tells us that sodium 2 plus is unfavorable. Sodium plus is no problem. We could do sodium plus, but sodium 2 plus, have you seen the sodium 2 plus cation? No. It would cost you way too much energy. Whereas we've seen magnesium 2 plus. We've seen magnesium 2 plus, no problem, because magnesium 2 plus is its most common charge. But have we seen magnesium 3 plus? No, because look at, to go from magnesium plus 1 to magnesium plus 2, the ionization energy about doubles. But to go from magnesium plus 2 to magnesium plus 3, it went up significantly, like what, 5-fold or something? And so there's a significant increase. Here we see aluminum 3 plus all the time. So to go from aluminum to aluminum plus, I1 is about 600. To go from aluminum plus 1 to plus 2 is about another 2,000. And to go from aluminum plus 2 to aluminum plus 3 is another 3,000. So altogether, 5,600. Over 5,000 kilojoules to go to aluminum 3 plus. But to go from aluminum 3 plus to aluminum 4 plus, it's a huge amount of energy. And so what we see here is this. We see the difference between valence electrons versus core electrons. To ionize valence electrons, the energies are relatively small compared to ionizing core electrons, like you can see here. And so this border that's shown here is the difference. And so this is what gives us this pattern, the pattern that we saw earlier. Here. It's going to stop here. Stop when we get to the noble gas, because to go beyond that, to increase the charge further, would cost way too much energy. So. Let's go back here. So eventually, we go silicon plus 4, but phosphorus plus 5, that's going to be a difficult ion, because if you look at the energy to get a phosphorus plus 5, although you can get an oxidation state of plus 5, but to get a free ion. What I mean by oxidation state and free ion are different things. When I'm talking about oxidation state, there could be other stuff in there. And so +5 oxidation state on phosphorus is no big deal. So in phosphate, for example, phosphate, phosphorus is +5. But as a free ion, do we see this? A phosphorus +5 free ion? No. That's too high of a charge. This would be just way too reactive. But here, it's okay because the +5 charge is going to be stabilized by having the oxygens there. You know, the oxygen is going to be -2. Everything's bonded together. And so, to get a +5 free ion would cost you a lot of energy. You know, all this energy here. You got to add it up. This is Hess's law. Oops. I'll do that. It's like Hess's law. You know, add up I1, I2, I3, I4, I5. Yeah. Look at chlorine. If you get chlorine +7, it's going to cost you a huge amount of energy. Chlorine +7, the oxidation state's possible, but chlorine +7 is what we call highly electron poor, right? Really electron poor. Argon would only cost you about 1,500 kilojoules per mole to take the first electron off argon. So argon is what they call a noble gas. A noble gas is a relatively inert. But argon, you know, you can get to react if you have an oxidizer capable of stripping an electron off with that much energy. This is valence electrons for the third row. We look at the first ionization energies. You see the blips here. You know, here's the blip with the 2p. The blip for the paired electron isn't so big here. You know, we expect it to go up, but it went down a little bit. Not much. Electron-electron pairing for a 3p orbital is less significant than electron-electron pairing for a 2p orbital, based on the size. You know, 3p orbital is bigger. Okay, those are ionization energies. We have something called electron affinity as well. Electron affinity is just taking a neutral atom, like fluorine gas, and adding an electron, which is going to make fluorine minus. The EA here, is this exothermic or endothermic? It's exothermic, so it's going down in energy. It's going down in energy, telling me which one's more stable, fluorine gas or fluoride. Fluoride is more stable because it goes down in energy. And so even though this is negative, we call this a high electron affinity. Affinity just means like or love for electrons, affinity. And so fluorine, of course, loves electrons. And therefore, this is high, minus 328. Which would be higher, minus 400 or minus 200 or 300? Which is higher, minus 400 or minus 200? Minus 400 is higher. And so here we can see in terms of electron configuration, fluorine's one electron shy of having an octet. Here. Let's see that, a completed octet there. Okay. That's electron affinity. So let's take a look at the electron affinities. Which species should have the highest electron affinity? Fluorine. Right. Fluorine should have the highest electron affinity. Helium, take a look. The helium electron affinity is positive, meaning it becomes less stable if it takes on an electron. In fact, look at all the noble gases. All the noble gases have an endothermic or positive electron affinity, saying, you know, if you add an electron to these species, they're going to go up in energy, which is destabilizing. But when we look at the numbers here, this is odd because look at sodium. Does sodium want an electron? No, sodium usually loses an electron, right? And so, but you look at the electron affinity, it's exothermic, just slightly exothermic, meaning that it can take an electron. This is in the gaseous phase. It's a little odd. But in general, the electron affinities increase as you go up and right, except you have to eliminate the noble gases. And so it kind of makes sense because the smaller, the higher the Z effective, right? Except for one exception. You have to know this exception here. It turns out that fluorine doesn't have the highest electron affinity. Which species has the highest electron affinity? Chlorine. Chlorine has the highest electron affinity. Now, why is that? Well, which one is you know what electronegativity is? Electronegativity is the ability to attract an electron. And it turns out that which one has a higher ability to attract electrons? Fluorine. Fluorine has a higher ability to attract electrons. But electron affinity is a composite of two things. One, the ability to attract an electron, and two, the ability to hold on to the electron. And so it turns out that chlorine has the best compromise there, because it still has a decent ability to attract electrons. You know, chlorine's a powerful oxidizer. But it has an easier time of holding on to the electron. It has an easier time of holding on to the electron because a 3p orbital is larger than a 2p orbital. Since the 3p orbital is larger, it can accommodate the electron with less electron-electron repulsions. And so the reason why chlorine has a higher electron affinity is because it has a larger p orbital. A larger p orbital means it can hold on to it. And so here, if we go back to fluorine, fluorine gains the electron, it goes into a 2p orbital. It's kind of crowded. But if chlorine gains an electron, it goes into a 3p orbital, which is less crowded. And that's it. But, you know, does that make any impact on how we think about oxidizers and reducers? No. You know, fluorine still is a way more powerful oxidizer than chlorine is. And so this is, you know, this we use for thermodynamic calculations when we do Hess's law and that type of stuff, when we're trying to figure out energies. But other than that, as conceptually, that we still think of fluorine as being much more reactive than chlorine. Okay? The thermodynamics, the energetics of this is going to be a little different. Okay. If you look at the electron affinities, you see, you know, in general, as you go up and right, we have higher electron affinity. But there's this drop here, you know, when we go potassium to calcium. So when we go from first row to, or first group 1 to group 2 here, there's a drop. You know why? What do you think causes this drop here? So going from lithium to beryllium, well, here, lithium, when it gains an electron, if lithium gains an electron, then that electron goes into the 2s orbital. And that gives us 2 electrons in the 2s orbital. When beryllium gains an electron, what orbital does it go into? The 2p orbital. And so again, this is not as stable because 2p's, are they as penetrating as 2s orbitals? No. 2p orbitals aren't as penetrating. And we'll go back here and look. 2p orbitals aren't as penetrating as 2s orbitals. You could, oops, what's going on? You could see it here. You know, the 2p orbitals in green, the 2s orbitals in blue. You might think, hey, wait a minute, the 2p seems to be more penetrating. The 2p seems to be closer to the nucleus overall, right? And so the green looks like it's penetrating more towards the nucleus than the blue. But the reason why the blue wins out, can you tell me why the blue wins out? It's because of this blip here, right at the nucleus. Do you see that? Because of this little thing here, we're going to say the 2s is much more penetrating than the 2p. You see that? And so take a look at those there. See. Okay, that's electron affinity. And so here we have oxygen. You know, oxygen, this is EA1. EA1 is to form the O minus ion, which is minus 141 kilojoules. So that's, is that favorable or unfavorable, minus 141? It's favorable. It's exothermic. Exothermic's favorable. But if we go from O minus 1 to O minus 2, we call this EA2, electron affinity 2. And so O minus 1 to O minus 2 is plus 744. Is that favorable or unfavorable? Unfavorable. So why is it that we form O2 minus and not O minus? Oxygen wants 2 electrons, right? But when we look at it, to gain 2 electrons, we have to do this. We have to add these together, like Hess's law. If we add these together, it comes out to 600 kilojoules. Positive 600 kilojoules. So if it's going to cost you 600 kilojoules, why bother? You know? Why bother? And so this is like if somebody said, okay, I'm going to pay you $141, right? And then you're going to pay me $744. Does that sound like a good deal to you? It doesn't sound like a good deal. It sounds like, why bother? I'd rather stop after being paid $141 and then call it, right? But here, it doesn't stop. It goes on, and oxygen ends up paying 600 kilojoules. Why? The reason why is because we aren't looking at the overall picture. The reason why, and this, we have to go back to this because of ionization energy. Look, in order to form Mg2+, how much energy is that going to cost? Magnesium is going to have to pay 700, and then another 1,400. So altogether, over 2,100 kilojoules. So that's like, okay, magnesium, you pay me $2,100, over $2,100 to go from magnesium to magnesium 2+. Would you want to do that? No, why bother? Why not just stay as magnesium? If you stay as magnesium, then you have $2,100 left in the bank. And so why would it do that? In fact, if we look at this, let's take a look at the energies here. So we go from magnesium to magnesium 2+. How much energy is that going to cost you? Well, 737.7 plus 1451. 737.7 plus 1451. 2188.7. 2188.7 kilojoules. Now that's our delta H there. Or ionization energy 1 plus ionization energy 2. And then for oxygen, to go from oxygen gas to oxygen gas 2 minus, delta H is going to be about plus 600. Is that it? Let's figure that out. 603. 603. 603 kilojoules. So altogether, you know, the cost of this is going to be kind of expensive. 28.91 or 27.91 kilojoules. And so why bother? It costs a lot of energy. The reason is because of this. Even though it costs a lot of energy, you get a lot of energy in return from the bonds. And so this is actually in the latter chapter. But let's take a look at the reason just briefly here. We don't really see the reason until later. So let me show it to you now. It's not coming up. It's because of this. What we form is this. When we take the magnesium ions and the oxide ions and bring them together, we form what's called the magnesium oxide lattice or crystal. When we form this crystal, a tremendous amount of energy is released in forming the bonds. The reason why we do this, why magnesium oxide forms magnesium 2+ and oxide, is to maximize the bonding here. Because the higher the charge, let's say if we just stopped, for example, if we just stopped at why don't we just stop at O-1? If we stop at O-1, it only costs us 141 kilojoules. And then why don't we stop at Mg+1? If we stop at Mg+1, it only costs us 737.7. And so that costs less energy. Minus 141 plus 737 is only going to cost us 600 kilojoules versus 2,800 kilojoules. So why not stop here? Because if we went from Mg plus O to Mg+1 plus O minus, the delta H for this, using Hess's law, is going to be about 600 kilojoules. 600 kilojoules versus 2,800. And then just build the lattice using magnesium +1s and oxygen -1s. Here, we build this lattice using that. Let's see if we have some other images of the lattice here. Let's see.
So in order to calculate the lattice energy, we need the E
Okay.
equation.
We'll just skip the lattice energy tutorial. All right. Let's see images here. So this is it. so when we form this, we got the magnesium ions here, the oxide ions here, we bring them together. But if we did this, if we built this exact same lattice, like this, as a crystal, with magnesium +1 and oxygen -1, it would cost us 2,200 fewer kilojoules. If you could save, let's say, here, somebody might say, okay, this option's only going to cost you $600. That option's going to cost you $2,800. Then you might go, well, why don't I just build the lattice with +1 and -1 ions instead of +2 and -2 ions? Why not just do that? They'll get the same lattice, right? It's like this, you might think of the same thing, If you have a choice, you could build your barbecue out of stainless steel, or your cooktop out of stainless steel, or you could just use regular steel. If you use regular steel, you're going to save a lot of money. Why not just use regular steel? Or, there are other options too. Like, for example, our tongs. We have stainless steel tongs and regular tongs. Which one do you think we have in the department? We have the regular steel tongs. They're cheaper. You have the regular steel tongs, but one of the problems with the regular steel tongs is what? They start to rust, And so the situation is sometimes it's better to spend more money in the long run, even though initially it's going to cost you a lot more. So here, we could build the lattice. The lattice is just putting together the ions. So if we're putting together the ions, let's just build the lattice using +1 for magnesium and -1 for oxygen. Build the exact same lattice. All I have to do is erase the 2. If I erase the 2 here and the 2 here and just call this Mg plus and O minus, how much money have I just saved? Like, I've saved $2,200, right? If we use money for this instead. That's pretty good. Save a lot of money. And so that's a cheaper option. But are there any drawbacks? Sometimes the cheaper option's fine. Sometimes the cheaper option, you get a better quality product in the end, right? But oftentimes you buy the cheaper option, you get a lower quality product. And so in this case, if we opt for the cheaper option, which is just using Mg +1 and O -1, are we going to get a cheaper product, or are we going to get the same product? Versus Mg2+. You guys know what I'm talking about here? So I just leave it at +1 and -1, and I say, okay, it's too much work to do the rest. I'll save $2,200. And then I'm going to build my crystal using +1 and -1 ions instead of +2 and -2 ions. And then I go, okay, what do you think? Maybe I'll sell it to you for the same price as the +2 and -2. Make a much bigger profit. But are you going to get the same product, or are you going to get a cheaper product? Well, what does Coulomb's law tell you? What does Coulomb's law say? Can you apply Coulomb's law to this instance? Apply Coulomb's law to this instance, and then tell me what your conclusion is. Let's see if you can apply Coulomb's law to this kind of scenario. You see Coulomb's law here? So what does Coulomb's law depend on?
Charges.
The charges. And so if I have plus 1 and minus 1, plus 1 and minus 1, versus plus 2 and minus 2, what difference does it make in the force? How much stronger? 2 times stronger? 4 times actually, because we have to double both. We double both the positive charge here and the negative. And so it's 4 times stronger, the bond is. And so this is the reason why. If we go from plus 1 to minus 1, it's a very weak lattice. And if we go from to plus 2 to minus 2, it's at least like 4 times stronger. 4 times stronger, roughly, ignoring the size. Well, hey, if it's 4 times stronger, let's go the other way. Let's go to plus 3 and minus 3. If I do plus 3 and minus 3, how many times stronger is it? 9 times stronger. 9 times stronger, plus 3 and minus 3. We should do it. If we build MgO using plus 3 and minus 3 for magnesium and oxygen, we get an extremely strong lattice. 9 times stronger than plus 1 and minus 1. 9 times stronger. So, well, 9 times stronger, but at what cost? And so if we look at the ionization energy 3, then it's going to cost us another 7,800, 7,700 kilojoules. So do you think going to plus 3 for magnesium, although plus 3 for magnesium in building MgO is very good, but as far as ionizing it is very hard. And so do you see it's going to cost just too much energy? Even though, yes, a plus 3 would be much better, it costs too much energy. And so what's going to happen is it's going to stop there. And so, yeah, this costs more. This costs twice as much energy, right? But it's worth it because we're going to get 4 times stronger lattice kind of thing. You know? And so this cost versus benefit is something that's done. But to go to plus 3 is going to be way too costly. And so even though MgO would be a much more stable crystal, if it were plus 3 and minus 3, forming those ions would be too expensive, and therefore it's not done. And so what nature does is this. You know, some people say, okay, metals want to lose electrons. Do they want to lose electrons? No, not really. Metals don't want to lose electrons because it's going to cost energy. You know, in order for the metal to lose electrons, you're going to have to expend quite a bit of energy. Even sodium. Sodium is going to cost you 500 kilojoules per mole just to take that electron away. Does sodium want to lose that electron? Is it giving it away? No. Something has to take it. What takes it is the oxidizer's got to take that electron. And so overall, it's going to cost some energy. You know. Well, chlorine's happy to take that electron away. EA1 for chlorine's pretty good, minus 349. So chlorine takes an electron away from sodium, minus 349. But is it going to pay enough? Chlorine's going to pay $350. Sodium is going to cost $500. Is it enough? It's not enough, right? Still plus $150. Where's that plus $150 going to come from? It's going to come from the bonds. Now, sodium chloride lattice looks like this, actually. Very similar to, I mean, this would be sodium fluoride, but you just put chlorides in there instead. Fluoride and oxide are about the same. This is what this slide is showing is that magnesium oxide lattice is going to be like twice as strong as the sodium chloride lattice. The sizes, well, the sizes aren't exactly the same. They're roughly twice as strong. Well, actually, no, 4 times as strong. Wow. Well, anyway, sodium chloride would be like this. Still cost you energy, but you get energy in return from building this lattice. Okay. And so the lattices we talk about later in the book. And so the energies don't add up. They don't add up because we aren't talking about the final end result. This seems quite unfavorable. This is not what you learn. You learn that oxygen wants 2 electrons. Does it really want 2 electrons if it's going to cost 600 kilojoules? Not in the gas phase, it doesn't want it. But if you form the solid, yes, it does. The solid, you're going to get a lot of energy in return. Now, how much energy are you going to get in return? Well, let me tell you how much energy you get in return. And so I need to just do one more search here. Let's just do MgO lattice energy. The lattice energy is the energy that we get back in return. I don't want the video. The MgOs, take a look at the top. You see at the top it says Mg2 plus, gas, O2 minus, gas. So we're there at plus 2200 kilojoules, which is cosmos. And then we drop all the way down here to MgO solid. That's going to release 3,845. And so it costs us $2,800, but we get $3,800 back in return. And so net, we come out ahead $1,000. That's pretty good, right? That's why it does it. It's to maximize the return on energy. That's what it does. Okay, now that's electron affinities. Now we're going to move on to magnetic properties. Magnetic properties, we have 3. We have diamagnetic. In diamagnetic atoms or ions, all the electrons are paired. And so when we look, there are no unpaired electrons in any orbitals. And these are weakly repelled by magnetic fields. In paramagnetic atoms or ions, there's unpaired electrons. And these are attracted to external magnetic fields. In fact, the more unpaired electrons we have, the stronger the attraction is. And you can measure the attraction to determine how many unpaired electrons there are. There's one more magnetic property. It's called ferromagnetic. Let's take a look at ferromagnetic really quick here. I have to go back to the book to do that. Because ferromagnetic is not discussed in the book still has not loaded. I can't believe that. I'll try one more time. I'll give up on the book if it doesn't load. Okay, it's finally loading. Lattice energies are talked about in chapter, let me see what chapter that is. Chapter 12. Ferromagnetic is talked about in chapter 23. Ferromagnetism. Ferromagnetism is when you have unpaired electrons and they organize themselves so that there's a net magnetic, what we call net magnetic. In the usual paramagnetic material, you know, there's an atom here, and they're randomly oriented, you know, where the North Pole is and the South Pole is. But in ferromagnetic materials, they aren't randomly oriented. You have domains, magnetic domains, in which the magnets all align themselves together. So that's ferromagnetic. So this blue is paramagnetism, the red is ferromagnetism. This is chapter 23. So we have that diamagnetic, paramagnetic, and ferromagnetic materials. Manganese 2 plus is highly paramagnetic. There are 5 unpaired electrons there, making it very paramagnetic. And that means manganese 2 plus is going to be attracted to magnetic fields. Whereas neon had all the electrons are paired up in neon. making them uninterrupted. And so this magnetic materials. There's something else called polarizability. Polarizability is how easy the electron cloud is to distort. You know, the bigger the cloud, the more polarizable it is. You know, the easier it is to distort. The smaller the electron cloud, the harder it is to polarize. And polarizability is, you know, big atoms are easy to polarize, small atoms are hard to polarize, and that is distort the magnetic field. Distort the electron cloud. So they're distorting it by putting an electric field here, a positive plate and a negative plate. And the electron's going to be attracted to the positive plate, so that distorts the cloud. Yeah. Polarizability increases with the size of the atom, you know, like was mentioned. You know, the bigger the orbital is, the easier it is to polarize. And so the bigger the atom, the easier it is to polarize. So cesium is big atom. Cesium is, you know, for cesium and francium are the biggest atoms on the periodic table. You can see that's highly polarizable. There's a polarizability in atomic volume. So the bigger the atom, the easier it is to polarize. So cesium. Small atoms like here, helium, hydrogen, those are harder to polarize. So let's polarize. Polarizability we talk about later. So here's a little summary chart. Ionization energies, top right, highest. Radius, you know, the smallest or at the bottom left, biggest, biggest ionization energies, top right. Biggest radii, bottom left. Smallest radii, top right. It turns out that there's one more periodic property, metallic character. Cesium and francium are also the most metallic elements on the periodic table. Metallic being easy to ionize. They have the lowest ionization. The most non-metallic are going to be like fluorine. We got the noble gases. All right. That's the end of the chapter for chapter 9. Chapter 9 is actually a pretty short chapter. Chapter 10 is a bit longer. Chapter 10 talks about bonding. And so let's take a peek at chapter 10 here. Grab the PowerPoints. I don't think I got those yet. Download chapter 10. Chapter 10 starts off with Lewis structures. 10 and 11 deal with bonding and Lewis structures and that type of stuff. So we'll start off in chapter 10. This is something we're going to see in chapter 10 and chapter 11. These are called electrostatic potential diagrams. Electrostatic potential diagrams, they look at the overall electron cloud. And then they look at rich regions of the electron cloud. The rich regions of the electron cloud are blue or red. You know, if you have lots of electron cloud, electron density around there, you know, is it coded as blue or red? What do you think intuitively, if something is rich in electron density, and dots, let's say? This is looking at all the orbitals, composite, just looking at the electron cloud itself. Would you say you would instinctively, green is just normal density, but the rich regions of electron density are coded as what color, blue or red? What do you think? Red? Red's correct. You know, for me, I would think blue, but red. And so when I look at electron cloud like this, I see this is kind of rich in electron density. And over here, this is kind of poor in electron density. And green is kind of just even in terms of electron density. Take a look at this one on the left here. looks like this red region and the blue region are a little bit more intense than the one on the right here. Lewis, this is Lewis here. You know, and when we look at Lewis theory is looking just at the valence electrons. You know. Oops, I didn't do that. Valence electrons play a fundamental role in chemical bonding. I need one of those pointers. And so Lewis, when we draw Lewis symbols just show the valence electrons. Lewis symbols never show the core electrons. So carbon has 6 total electrons, but only 4 valence. Electron transfer leads to ionic bonds. Sharing of electrons leads to covalent bonds. And so we know that ionic bonds are what we call winner-take-all. Covalent bonds are shared. Electrons are transferred or shared to give each atom a noble gas configuration, the octet. That's Lewis. So we can do some reactions. These are Lewis symbols here. Silicon, we ignore all the core electrons. Silicon just has 4. We write them singly like this. We divide the atom into like 4 regions usually. And so nitrogen is 5, so we divide it into 4 regions and we got a pair one out. This is like phosphorus, arsenic, antimony, bismuth. All these have 5. This is all the same family. This is a nitrogen family. This is going down. You know, nitrogen's small, bismuth is going to be big as we go down. This is the 2nd, 3rd, 4th, 5th, 6th period, 6th shell. Aluminum, this is going across selenium, iodine, argon. Argon has an octet, you see. An octet is what we strive for, so we strive for 8 electrons here, unless it's hydrogen. If it's hydrogen or helium, we strive for a duet, which is 2. But octet, you know, sometimes we can exceed octets as well. Here's creation of ionic bond. Creation, if we have sodium and chlorine react, you know, this forms a lattice. Remember the lattice? And so this is just showing one of the ionic bonds, but in reality, there's a heck of a lot. I mean, if this is a mole, we've got a lot of bonds. It's not just one. This is why lattices are so, oops. So, this is why lattices are so, you know, if I look at the sodium and fluoride, sodium fluoride, how many ionic bonds do you see right there? I see 1, 2, 3, 4, 5. And there's a 6th one on top. So each sodium is actually ionically bonded to 6 fluorides. And each fluoride is ionically bonded to how many sodiums? 6. This is a lattice. You don't really see it here because we're ignoring most of the lattice. When we look at the PowerPoint here, we're just seeing one of the 6 bonds right here, kind of thing. In a mole, you know, if we had a mole. But actually, it turns out the bonding is even a little bit more. I'm oversimplifying it too, because the bonding is a little bit more than that. It's a lattice of bonds, not just 6. It's even more than 6 bonds. Well, we're not going to get into it until we hit chapter 12, so I'm going to skip that for right now. Essentially, an electron, this electron's marked X. Sodium has 1 valence electron. The valence electron is taken by chlorine. We form the sodium ion and chloride. This is what we call the Lewis structure for an ionic compound. The Lewis structure for an ionic compound shows no line. You see there's no line for the bond. The bond is between the positive sodium ion and the negative chloride ion. That's ionic. Whereas a covalent compound like this forms a covalent compound. We show a bond. The bond is either shown as two dots or a dot and an X. The X usually shows a dot, or a line. A line represents 2 electrons. And so the Lewis structure is totally different. Lewis structure for an ionic compound, Lewis structure for a covalent compound. Can you draw the Lewis structure for, how about magnesium chloride? Okay, so you should have something like this. We don't show a line again because it's ionic. And so magnesium has 2 valence electrons, chlorine has 7 each. And so it forms something like this. This is going to represent this, you know, the magnesium chloride lattice, in which we have magnesium ions and chloride ions packed together. Crystalline lattice like this. Let's see, this is also shown like this as well. This is showing lines. It's just showing lines to show, you know, the nearest neighbors and interconnectivity. But the lines aren't representing bonds here. The lines are just representing covalent bonds, I should say. The lines are just representing connectivity. These are all ionically bonded. Although we could have lattices like this that are covalently bound as well. So, did you get something like that? This is different, you know, than something like CO2. You know, we gotta look at CO2. Looks slightly different. And so this is an ionic bond. And the bond is 100% ionic. Even though we say this is 100% ionic bonding, there's a little bit of covalent interaction in there, but we don't have to worry about this until later. This is sodium chloride. Magnesium oxide has the same structure, but magnesium chloride, because of the 1:2 ratio, has a different structure. No covalent bonding here. And so we should see sharing. This would be OCl2, which forms from oxygen, needs 2 chlorine. So we have a sharing. Sharing, we get an octet, 8, 8, and 8. Water, we have an octet around oxygen, we have a duet around hydrogen. Hydrogen, we have duets. Chlorine, we have octets here. 3 lone pairs, 1 bond pair. Gives us a total of 8. We have other types of bonds too, coordinate covalent bonds. Have you ever heard the word coordinate covalent bonds? Coordinate covalent bonds is, if we go back over here, take a look at all these covalent bonds. One thing all these covalent bonds show is that they show 1 electron coming from atom A, 1 electron coming from atom B. 1 electron from atom A, 1 electron from atom B. And so both atoms contribute 1 electron or more to the bond, you know, but both are contributors. In coordinate covalent bonds, they aren't. 1 electron supplies all the bonds. So, for example, in ammonium like that, we have ammonia. Ammonia has a Lewis structure like this. And then we have an H+. Does H+ have any electrons to... H+ doesn't have any electrons to share. So what happens is, well, there's still an attraction here. So this lone pair will bond there. And what results is a coordinate covalent bond. That is, did H+ contribute 1 electron? And nitrogen contribute? No. Both electrons came from nitrogen. Both electrons came from nitrogen, then we call it coordinate covalent or dative bond. Once this bond forms, you can't tell the difference. All 4 bonds look exactly the same, so you couldn't tell. You can't tell the difference. Same thing in hydronium. There's a positive charge in this thing, but it's taking water and adding an H+ to it. We get hydronium. Yeah. Another coordinate covalent. This is the formation of ammonium chloride here. You can see coordinate covalent bonds in a form here. This lone pair, you know, attacks this hydrogen. This is what we call Bronsted, you know, proton donor, proton acceptor. We also call it Lewis. This is a Lewis because we have an electron pair donor. The electron pair donor grabs the hydrogen. These electron pairs are left on the chlorine. So we form ammonium ion and chloride ion. That would form an ionic lattice, similar to like sodium chloride. And so this formation of ammonium. Here, sometimes we have to form multiple bonds to get the right octet. So here, this shows the formation of a double bond here, and a double bond here. Otherwise, we can't get an octet. If we just form single bonds here, then oxygen is a total of 7, carbon has a total of 7, and this oxygen has total of 7, so for multiple bonds, complete octet. Nitrogen, triple bond, you can get the octet. Yeah. Oxygen will form a double bond, but something strange happens here. If we form a double bond, are there any unpaired electrons here? Oxygen, like nitrogen, should be diamagnetic. In fact, this should be diamagnetic. All the electrons are paired, you know, a pair here, bonding pair here, bonding pair, lone pair, paired. CO2 is diamagnetic. In fact, CO2 is diamagnetic. Nitrogen is diamagnetic. This is showing oxygen. This is liquid oxygen. This is a big magnet here. And what's happening with liquid oxygen? Liquid oxygen is getting trapped by the magnetic field here. So liquid oxygen stuck in the magnetic field. And what that means is that oxygen is not diamagnetic. Oxygen is paramagnetic. But what are the unpaired electrons? When we look at Lewis structure, there are no unpaired electrons in Lewis structure. And so, you know what? This means that there's something wrong. There's something wrong with Lewis theory, or there's something wrong with magnetic properties of oxygen. It turns out there's something wrong with Lewis theory. That's something that's wrong with Lewis theory we aren't going to discuss just yet, because Lewis theory, for the most part, gives us the correct answers. And sometimes it's wrong. But we aren't going to abandon it because it's so useful, it's handy, and it's easy. And we're going to talk about this in a lot more detail later. And so this is just a little preview for right now. You know, there are other things that are attracted to magnetic fields and electric fields as well. Let's see, like this. And so we don't want to get confused. Sometimes it's easy to get confused because there are going to be things like a stream of water. Have you seen this? Not this. Here, I want to. Oops. Okay, here we go. Sorry, this is not the one I wanted. This is the one. Well, anyway, this is the one I wanted here. You can see there's a stream of water here. Oops. A stream of water coming out here. Do you see it's bent, this stream of water? It's bent towards this bar. This bar is either positively charged or negatively charged. So the water is being bent towards this. This is an electrostatic attraction. This is not a magnetic attraction. You know, here, well, it could be as well as magnetic, but this is primarily electrical because water molecules are polar, so there's a positive end and a negative end. Whereas this oxygen thing is different. Oxygen is not polar, so it's not being attracted to a charge or anything like that. And so it's different. Here we can see polarity here. And so like water, ammonia would show the same thing. If I had a rod or a bar that was positively charged or negatively charged, ammonia molecules would be attracted to it as well, because when we look at the map. This is the map of the ammonia here. And when we look at the map, electrostatic potential map, that is, we see that we have electron-rich region here and electron-poor region here. Electron-rich region would be delta minus, an extra negative charge. Electron-poor region would be delta plus. And so if I had a positive plate here, then the red end would be attracted to that. And if it's strong enough, it'd be pulled towards it. And so ammonia would be like water in that sense. It's very polar there. But how these maps are determined is you move a probe in, and then you get some electrical resistance, and then you stop, and then you map it out. And we do this. This is done from theoretical. You could also do this. These maps are generated from theory, but you could also generate what we call dipoles from experimental measurements and simple calculations. And so here we can see like sodium chloride. You can see sodium chloride. This is highly ionic. In fact, sodium chloride should be ionic. And so the chloride should be negative, which is the red, and the sodium should be positive, which is blue. And so here we have the sodium chloride. This would be a molecule of gas. Compared to HCl, HCl is much less polar. If you look at chlorine, it's non-polar. It's all green. You see that? And so we can see the polarity. As we increase the polarity, we say we increase the percent ionic character. And so the more polar it is, the more ionic it is. The less polar it is, the more covalent it is. And so this would be something like close to 100, actually chlorine's 100% covalent. And this would be close to 100% ionic, although not quite there. And so we can see the differences here in terms of potentials. We have one more thing is electronegativity. Electronegativity and electron affinity are similar. Electronegativity is just the ability to attract, not the ability to attract and hold. And so fluorine is going to be at the top of the list for electronegativity. Fluorine gets a 4O. Chlorine's a 3O. And so even though chlorine has a higher electron affinity, its ability to attract isn't nearly as strong as fluorine. And so this is electronegativity. This is Pauling stable electronegativity. Francium has the lowest at 0.7 here. And so electronegativities range from 0.7 to 4.0 on the periodic table. All right, I'm going to stop here and then continue.